here. Oh yeah, okay, nice. So now it's recording. And let me screen. Okay, cool. There we go. Now you should be able to see that. So yeah, so if you remember, this is chapter 15, and the textbook, I guess, calls it something like conjugated. It's something sort of to do with like conjugated systems. Okay. It's like a kind of weird way to put it, or a weird place to have it, because like so much of the later reactions you'll see in this course have to do with conjugated systems. For example, chapter 16 is going to start being all about aromatic rings, which are like about as conjugated as you could get. And then let's see, sometime around, I think like chapter 20 or something, you'll see like Michael edition, which is all about conjugated systems yet again. So, you know, it's like a kind of common thing that comes up in this course, is the idea that things are conjugated. All right. And like when it comes to conjugated systems, in terms of doing reactions, a really important thing is to know about molecular orbital theory. My handwriting is being a bit messy today. So molecular orbital theory, right? And in the case of the things that we're working on, we can have like, let's say the really simple case is where we have 4 atoms. And then what you want to do is for each atom, you'll draw out your molecule that number of times. Okay, so there are 4 atoms, and so you draw these out 4 times. All right, you draw an up arrow for energy. Okay, and then you count up from 0 like this. Okay, so let's break this down. Okay, so there are 4 atoms, which means that there can be 4 molecular orbitals here. Okay, and we just draw them out in terms of the molecule because we want to know what they look like so we can do something with them. And then we count up from the bottom starting from 0, and that's going to be the number of nodes. So here there's 0 nodes. Okay, and so we draw in our orbitals, and these are all plus, and these guys are all minus down here. Okay, no nodes. The sign never changes. So always on top is plus and always on bottom is minus. Okay, down here, there's 1 node because it's the next one up. Up here, there are 2 nodes, which would go, I don't know, probably like here. Yeah. Okay. And then up here, there's 1 node for each atom, right? And it doesn't matter which side you pick to be plus or minus, as long as you flip every time there's a node. Okay. Plus, 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 right? And so you flip every time. You don't have to draw these atoms as being bent like this. You don't have to try to like make things complicated. Like you could actually just draw like, you know, something like this. It's kind of like ugly, and you should like draw these dots instead. You could do something like that, but there's no, you don't really need to. Or it's nice to be able to see it in terms of like what the actual kind of structure of the molecule looks like. Okay, so that's like a good way of drawing the molecular orbitals, right? And then in case this diagram wasn't already getting busy enough, draw a big line halfway through. These are bonding. These are anti-bonding. Okay, and that's how you get all of them. Okay. So now I guess a question for you guys: how many electrons are in all of these orbitals combined?
16.
16. So if we count, let's see. So we get 2, 2, 2, 2, 2. Okay. These like figure eights that I drew, which are really like these kind of hourglass shapes, like this at each atom. These don't really this isn't like, so they don't hold one electron each. What they actually are is like a really like kind of, I don't know, weird and complicated thing to do with the wave function of the molecule. So that's not it. So it's not 16, it's actually a lot less.
4.
4, yeah. Yeah, exactly. So to get that number, all we do is we just count how many double bonds are contributing to this conjugated system. So it's just these two. Okay. And so maybe let me draw this out bigger. Oh, all right, maybe that's too big. There we go. Okay, this is good. Okay. And so again, we had increasing energy, right? And then, well, let's just go through it again, right? There we go. We draw in our nodes, and then this whole area is plus, and this whole thing is minus down here. And then we had a plus and minus, right? We had all this. Okay, and then we had our big line, which said this is anti-bonding and this is bonding. Okay, right? And so we fill in electrons. Each of these orbitals, as with any other orbital in all of chemistry, I think, can only hold 2 electrons. So we just fill in from the bottom. There's 2. There are 2. Okay, and these are just empty. Okay. So if we wanted, for example, to pull an electron from this molecule or from this conjugated system, we'd pull it from here. All right. And that's why we care about this orbital, because if we want to take an electron, this is the one we're going to pull it from. So that's why we give this a special name, which is called the HOMO, highest occupied, and then MO, molecular orbital. All right. And then over here, we give this another name because if we want to add an electron, it's going to have to be in that antibonding orbital or that empty orbital. Okay. So we also give this another name. What do we call this?
LUMO.
Yeah, so this is the LUMO, exactly. Lowest unoccupied molecular orbital. Okay. Cool.
Sorry, could you just explain on like the very bottom line, you have like 2 circles with a plus and minus, what those are?
Yeah, I was just getting really lazy, and when, yeah, so it's kind of like, so each of these will be like a plus on top, and each of these will be a minus on the bottom. And what happens, like, when you draw out these orbitals, these like figure eights, these are like the pi orbitals. Each of these up at the top is a plus. So they kind of all just mesh together. And they become like one big plus kind of blob, you could think of it. Okay. And same with the bottom. So this is just minus. And the same thing will happen up here. So these will form a kind of like full orbital thing. So this one will be plus, and this will be minus, and this will be minus, and this will be plus. Yeah, so the electrons can kind of just flow freely in this region. Sort of, yeah. Yeah, it's like, I mean, I guess it's worth saying and mentioning and just keeping in mind that this whole like drawing where we have these like pluses and minuses and that like we can kind of fill in like that. This is all to do with like the wave function of the molecule, which like isn't really physically meaningful. If you like take the wave function and like square it, then you get like the probability that electrons are in that space, but that's certainly more complicated than we need to worry about for this. Yeah. So when you do draw these out and, you know, if you do, leave yourself a ton of room so you could just, you know, you don't have to be so precise about drawing your loops. You could just like, you know, draw a bunch of like pluses like this, and then you'll be like, oh, look, there's a whole big like section of the orbital. But yeah, that's why like I said I was lazy and I kind of just drew a whole big thing. Because like they do combine to make one, and I just didn't feel like drawing out every plus and every minus. Yeah. Cool.
I had a quick question, just so I'm understanding. So whenever we're like when you ask the question, how many electrons are in all the orbitals? So we're talking obviously about pi electrons, and that's basically the number of like double bonds you have times 2.
Yeah.
Okay. Because then the other question I had was that's not necessarily going to be equivalent to the number of p orbitals. Because like if you had like a conjugate, like if you had a double bond and then you drew another carbon out, but it was a carb anion, you would technically have 3 p orbitals, but only 2 pi electrons.
So I was actually about to bring this up because so we could do this for conjugated systems, right? And like, you know, we could even think about like an example where we draw like 3 double bonds or something, right? And then you could go through and do the whole like 1 node and 0 nodes, and this is already a sloppy drawing, so I'm just not gonna keep going with it. But it doesn't have to be like perfectly, I don't know, like stable thing, right? It doesn't have to be even number of carbons. So we could do, for example, just an allylic anion, something like this, okay? And well, here, how many electrons are there? There's 2 in this double bond, and then over here, remember this minus charge. I mean, in organic chemistry, we're really just used to writing this sort of like charge with a circle around it, right? But if there's a minus charge on a carbon, that means it just has 2 free electrons floating around like that. Okay, and so what this means is there's another 2 electrons here, and so we have 4 total electrons, right? But here we go. Remember, we write out 3 of the molecule because there are 3 atoms. And then we go as normal. We write nodes. We start with 0 nodes, 1 node, and 2 nodes. Okay. And let me write the energy sign over here, right? Just to say, it's always good to show that we're going up in energy as we go up. Okay, and then we fill in. So plus, 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 minus, okay. And then, yeah, we could draw in these nice bubbles. Like this if we want, right? So we have plus and minus, and then this atom winds up being exactly on a node, so we don't write out signs for it. and then we get minus and plus over here. And so it's kind of just, maybe I should draw these as like figure eights so that it's more recognizable. Okay, and then plus, minus, plus. Okay, right, we get it. Yeah, and so now again we fill in electrons. We had 4 electrons, so we go and we fill in like this and like this. Okay. And then what's the next step?
Can you go over how you got 3 like levels?
Yeah, it's like the way that I always think about it, and well, I don't know if there is like another good way of going about it. I always just write the number of levels is equal to the number of atoms that are in the conjugated system. So just as like another example, let's say we had something like this right here. Well, we would write out this molecule 5 times. So, yeah, and the reason, I guess, that we can kind of think of, let's see, this note I guess would go over here, but that's kind of weird. The reason is because we want to be able to fill in with nodes up till we get a node between every atom. After that, you can't get like multiple nodes between 2 atoms because that's like, well, I don't really know how that would work out. So we want to be able to fill up to this point, and we start from 0. And so it'll always wind up being that the number of atoms is the number of energy levels that you wind up having.
So Adam, you may have already answered this, but like, let's say, and you don't have to draw this, but we have like nonene, for instance. So we have 9 carbons, but we only have 1 alkene. We would draw out like 9 levels, even though we're only filling that first orbital because we only have 1 pi bond.
So if there's only 1 pi bond, maybe I should have been clearer. You write out the number of levels of carbons that are involved in the conjugated system.
So in a nonene, for instance, how many carbons would be involved in that system?
If there's only 1 pi bond, then there's only 2 energy levels.
Okay, so then would you like sever the nonene to only be those carbons involved?
Yeah, you don't worry about the other ones.
Oh, okay.
So it would look like ethene then?
Yeah, with other carbons dangling off the side, but they're not involved because they don't have any pi bonds or pi orbitals even. So, yeah.
Okay, so then you would only have to draw 2 energy levels, or?
Yep.
Okay.
Yeah.
So there would just be the bonding and the anti-bonding. Those would be
Exactly.
the only levels involved. Okay, got it.
Yep. Yeah. So, for example, in this case, like in the previous one, just the one thing that we didn't mention. So we have everything here, and then we, as usual, we draw a line through the middle of the energy diagram, okay? And everything below is bonding, everything above is anti-bonding. And what happens to the orbital in the middle? Because one of them is exactly in the middle.
Non-bonding.
Exactly. Okay. So if you want a sort of rule of thumb is that you only get non-bonding orbitals when you have an odd number of atoms in your conjugated system. Okay. That rule is okay to hang on to for now, but it's a bit dangerous to use to take in general, because once you get rings, things get more complicated. And well, you're going to learn that in like 2 days. So be careful about how you use that. But when it comes to linear systems like this, then you only get non-bonding orbitals once there are an odd number of carbons. Okay. Yeah.
Just a quick question, kind of organizationally. I don't know if you know, or maybe somebody else in the class. Are we cutting the quiz topics the same as last time, where it's like only stuff that was on last lecture, or is stuff gonna be on the quiz that's on from this lecture coming this Tuesday?
I know Dr. Tong, on one of his slides in his lecture that he posted, it literally says like end of quiz 2 material.
Oh, that's cool. Where exactly did it end?
I think it was the end of the endo rule.
Okay, yeah. So all the way up through Diels-Alder.
Makes sense. Thank you.
Yeah. Unfortunate, you guys. Well, you're gonna get quizzed on Diels-Alder one way or another, and you might as well get it over with. Yeah. Okay.
Wait, I have a quick question for that bottom system. Is it right that you only have four electrons?
Yes.
4 pi electrons? Okay, great.
Exactly.
Thanks.
So these are all empty. If this were to be a minus charge, for example, well, then we would have 6, right? And I'm not going to draw out every molecule again, but we would have 6 electrons. And so this is bonding, non-bonding, and anti-bonding, like that. Yeah. Good. Okay.
Adam, sorry.
Yes.
Going back to the previous example that had 5 carbons and a positive charge, given that that positive charge was not there, how would the molecular orbital differ?
Yeah, good. Yeah, this is similar to what Dean was asking, and it's good to draw it out. So there are only 4 carbons in the conjugated system. Okay, and so we only have 4 different energy levels. Okay. And really this carbon here isn't involved in anything. It can't conjugate. It doesn't have a pi orbital, right? So we can kind of like, I don't know if that's like too confusing. I don't know like what a good way of drawing it is to say that carbon isn't actually involved in anything. I don't know, like.
Would it be safe to just not draw, like just draw it as kind of like a butane?
Yeah, I mean, in terms of working out this problem, it would be, because it's like whatever is on that end is really not involved, as long as it's not any other double bond stuff that's able to conjugate. Maybe if I draw it as like something like this. Yeah, I don't know what Dr. Tong would expect you to draw. It's like a sort of thing that doesn't contribute or matter. I guess if you want to be like proper, you should draw out the full molecule anyway, and then you just do all of the work without including it. So for example, we'll draw the one node here, and then here are the other nodes, right? And we draw the regular MO diagram for butane, but we only write our pluses and minuses and draw our big blobs for this side of the molecule. And this carbon over here is just left alone. We don't do anything with it. This is probably the proper way to do it. And I guess if you get asked, this is how you should draw it out. Just draw everything with the rest of the molecule there and just like don't do anything with it.
And sorry, really quickly, I think someone asked this before with the blobs. What do those indicate again?
Oh, there was a message in the chat. Okay. So the blobs are like, they're areas where the wave function is not zero. They're you can think about them as where the electrons will be. So these nodes, like the nodes have physical significance because they tell you there won't be any electrons in this spot. Like in this middle area of the molecule, really this is like a plane because it's like three-dimensional, right? So it says like in this plane here, oh, that was such a bad drawing. There won't be any electrons there. And all of the electrons, for example, in this orbital right here, all of the electrons will be on like either half of, well, each electron will be on either half of the molecular orbital.
Got it. Thank you.
Yeah. Okay. Yeah, it's like the kind of annoying thing is that like molecular orbitals don't really have much physical significance, or at least the signs or like the kind of the way you draw them don't have that much physical significance, pretty much with the exception of the Diels-Alder reaction. Like it's like the one place where it really matters. And the reasons that it does matter is like really high level stuff that is like way beyond the scope of this class, but you just have to know how they work and what they do. Right? And so here, okay, we can draw our blob. Okay, and then the top one too. Yeah. Yeah. Okay. So someone asked me in the chat, which I didn't have open previously, but I do now, whether all the sections have quizzes, because the person is actually not from Dr. Tong's class, but from Professor Perchek's class, and I don't know. You should follow what your class is doing. I think Perchek probably has just full exams instead of quizzes. Yeah. Okay. Okay. So let's see, a couple of other things that we saw this chapter. There's this idea which is new, but I think you'll see it a few more times. There's this idea of a kinetic versus thermodynamic product. Okay. And so kinetic means that you do it while things are cold. Okay, and in contrast, thermodynamic means that you do things while it's hot, right? And cold in organic chemistry means minus 80 degrees Celsius. Hot means anything like comparable to room temperature. So like above, I don't know, above like 40 degrees Celsius, or really anything around what room temperature would be. Okay. And so this mainly comes up in this idea that we can have, for example, this molecule right here, this like 2,3-butadiene or whatever, or what I'll leave you guys to do the naming. So if we take like, for example, no, this is the wrong molecule, isn't it? Yeah, so it should be for this like conjugated system. So if we add HBr while things are cold, what's going to happen? How is the HBr going to add?
To the more substituted side?
But they're equally substituted.
Oh,
Wouldn't it go to the least, or like the ends of it? So wait, something like that, yeah.
Okay, so there's an H here, and maybe let's think about what'll happen, right? So we'll get this H, right? This H plus. Okay, in both cases, the H plus will attack here. And so maybe let me not even write this out. This is just what happens every time, okay, when we add HBr. And there's this double bond over here. Okay, cool. And let's see, we had a plus charge over here. Remember, we had a neutral molecule and a plus charge that got added to it, so we have to retain that plus charge. Okay, now the questions. Go ahead.
I was just going to say, is that when our bromine will attack this positive charged internally?
So yeah, well, we can do two things here, right? We can choose to move this double bond, or we could just attack right now with the bromine. So let me pick two different colors. So I'll pick kinetic will be blue because it's cold. Okay. And so first thing we could do is just, well, okay, light goes to light, you know, opposites attract, I guess, right? So the bromine will go and it'll just fill in. Okay. And so we'll wind up getting this product. All right. And now let's say it's hot instead. And now this one's red. It's hot. What happens is that this electron pair is going to move over because there's more time, right? Things happen a lot faster when it's really hot in the solution. So the electrons will be able to move a lot faster. And so instead, this bromine is going to come in and attack on the end. And so that whole double bond will have shifted, and you'll get the bromine on the end. Okay, and so this is the thermodynamic product, and then the kinetic product is in blue. Okay.
So Adam, is there any point at which in the warm or hot instance where we have a positive charge on the terminal carbon, or is it all happening instantaneously where the bromine is attacking the end while the electrons are moving over?
Yeah, you will get a positive charge on the end.
Okay, got it.
Yeah. So maybe to write out the whole mechanism here. Yeah. So this double bond will move. It'll move over. So we'll move it here. There'll be a plus charge. And now the bromine goes in and attacks. Yeah.
Right. Thank you for that.
Mm-hmm. Yeah.
Is that considered then SN1? Because it's not concerted and you're forming a carbocation?
So remember, SN1 involves replacement or substitution. But in this case, we're just adding because we've gone from a double bond and added two things onto it, or onto the molecule as a whole. So it wouldn't count as SN1 because with SN1, we'd have to pull something off and put something else on.
Got it. And this is possible because it's the allylic position. And there's the carbocation.
Yeah. So the reason that we're able to move those electrons around is because we get an allylic carbocation. exactly.
Gotcha. Thanks.
And Adam, would you mind quickly doing a like a carbon chain with like allelic carbons on like one end? So like let's say we have like a nonane, and then only the first 4 carbons are involved in the alkene. I'm still having a hard time like understanding what to do with the rest of the alkane chain.
Exactly. Let me save this. Save. Okay. And make a new one. There we go. Okay. Cool. Yeah. So I guess here, actually, I'll just draw it like straight in the middle of the molecule. I don't know how many carbons this has. It has 8. Let's add a 9th for good measure. In this case, because this entire reaction has just to do with double bonds, there's no single bond play at all. It's like an unusual thing to say, but we really can ignore the rest of the molecule. So let's say, okay, well, in both cases, we know that the double bond will attack the H+, or the H+ will steal the electrons from the double bond. And so, sure, we'll write HBr there. Okay, let's write our big molecule. There's an H, and we get our plus. And there's that double bond, right? And now we have our 2 different conditions. So I think last time I did kinetic first, so let's do that again. Over here, this is at minus 80C. Okay, and I said earlier that the double bonds can't move around in time. I think in practice, it's actually more that the bromine can't move around in time, and it's just favorable for the bromine to sit on the first place that it can find, which right away is going to be this. Hence, that's why it's also called the kinetic product, is because the bromine just goes wherever it can right away. So there's that hydrogen, there's that bromine, and the double bond. And in the case of this the thermodynamic product, where it's hot, we can move this double bond over. Oh, very sloppy today. So there's the plus there. And then we're done.
And Adam, is there any preference for which alkene will attack the hydrogen? Because on one side of that molecule, there's like an ethane coming off, and the other side there's a butane coming off. Like on either side of either of those alkenes, would one of those prefer to attack the hydrogen, or is that?
Yeah, that's a really good question. In this case, no, because each of these double bonds has the same charge, sort of. So maybe let me give a different example. In a case like this, let's say like that. In a case like this, we know that the hydrogen is going to land on either of these 2. So there's A or B. And we know that the hydrogen is positive, right? So the question is, which of these 2 carbons, A or B, is more positive? Because the hydrogen doesn't want to go to the one that's more positive. It wants to go to the one that's more negative.
Would A be more positive?
I think so. No, let's think about that.
Wait, what do you mean by like more positive? Do you just mean like more electron density?
Yeah.
Because then in that case, wouldn't A have like more electron density?
Yeah, I guess it would, wouldn't it? Yeah. Yeah, so that makes me think that A would be the one to attack the hydrogen. Yeah.
Is this like rule called? Is there like a rule to this?
No. No. For this one there isn't. So how about this? Let's think about this in terms of resonance. So what if we move the electrons over? How did I draw this structure earlier? Like this. So if we move the electrons over like that, well, this positive charge will be fairly favorable. If we move the electrons the other way, then this negative charge will be really unfavorable and this positive charge will be really unfavorable. So this is the preferred resonance. And so that means that A is going to be more positive.
So we're really looking for carbocation stability.
Yeah,
Okay.
in terms of resonance. Yeah. Well,
Right.
yeah.
That makes sense.
So then would the top product be the thermodynamic one?
Oh, well, we haven't even done the reaction yet, which is where we were about to get to, right? So that means, so since A is more positive, that means that B will attack, right? Or let's say also B is more negative.
Also, so what Sophia was saying earlier, another way of saying that one is more positive, A provides a more stable carbocation.
Yeah,
Okay.
I think that would be fair. Right. And so B, oops. So the carbon B will attack the hydrogen. And so in that case, right, we'll get something like this because carbon B would attack. Okay. And then we do kinetic and thermodynamic the same way that we did earlier. Whew. We haven't even gotten to Diels-Alder yet. That's okay. So
I'm a little confused on the thermodynamic. Like the last one we did before this, why is that like movement of the double bond favorable? Or is it just like, does it just happen?
let's see. Also, actually, that is a good question. Maybe in this case, it doesn't matter as much as I was making it out to be. Maybe Dean's question actually had a lot thought to it and some parts that I wasn't considering. So the kinetic and thermodynamic product thing is normally considered in terms of 1,3-butadiene, which was this molecule I drew on the previous page. It's this guy. And yeah, I guess you're right. It's in here, the kinetic product is less energetically favorable because the double bond's on the end, and we like more substituted double bonds. All right. So when we have the thermodynamic product, we have all the energy we need that we can do some moving around, some shuffling, and we can get that more favorable double bond. In this case, though, the one up here, which Dean had asked about, in both cases, we wind up with a trans-substituted double bond, di-substituted double bond. Or maybe it doesn't have to be trans, it could be a cis di-substituted double bond. Doesn't make a ton of difference. Well, either way, it'll be the trans one, because if we're picking between cis or trans, then we'll pick trans because it's just better. But in both cases, we'll have this di-substituted double bond. So is this molecule over here really more stable than the other one? Maybe not so much.
Okay.
So since there is no favoring, you would just have both products, right?
Yeah, I guess so. In the case of this kinetic one, there's still not enough energy for you to like make a substantial amount of this product, because you still have to move things. You would still have to move things around. So when it is minus 80 C, you're still just primarily going to get this. Down here, you'll get plus. Yeah, you'll get the blue product as well.
For the last example of the one with like carbon A and carbon B, can you draw the final products?
Yeah, I can. Yeah, so in this case, oh, okay, this one also gets complicated. Yeah, maybe this is why I shouldn't come up with examples on the spot. So, okay, let's say the kinetic product. Well, that one we know exactly what's going to happen. Minus 80 C, right? Not enough energy to move things around very much, so we're just going to attach the bromine onto here. Okay, and the double bond is going to stay here. All right, let's say we're doing thermodynamic product. Well, we have a choice, right? We have this molecule or this, the one where we resonate. Okay. So I guess now the question is up to you guys. Which of these two is more stable? Is it going to be M or N?
N?
N is more stable?
M.
Ah,
Yeah, I agree. I think it'd be M.
yeah. Sorry, Dean. I would also agree. N is more stable because it's the more substituted double bond.
Okay.
Yeah. And so this is, oh, okay. More substituted. So this
I
is more
guess what's the
stable.
priority then? So I guess having a more substituted double bond is more important than having a more stable carbocation in this case.
Yes.
Okay.
Yeah. I think that's fair to say. Because the thermodynamic product is always going to take whatever the most stable product is. And so the fact that this product is more stable means that this is the one that you'll take as the thermodynamic product.
Okay, so even though the carbocation might be more stable in like what was N, the product winds up being less stable. So you okay, that makes sense.
Yeah.
So in this case, the kinetic and the thermodynamic products are the same?
Yes, I think so. Yeah. Yeah, I believe so. Yeah, Not 100% certain about this.
Wouldn't a tertiary bromide be more stable than having that secondary bromide?
Yeah, that's why I'm thinking that the whole point about the carbocation stability, in terms of the intermediate, that yeah, yeah, I'm not too certain that this is the thermodynamic product. It might be the other one. Yeah.
Because
This
wouldn't
is-
all these addition reactions be Markovnikov if we have a chance to make it so? Or I guess would that even like be a factor here since these are kind of weird reactions?
Yeah, these are.
Okay.
Yeah, it's weird, right? It's hard to say because you have the kind of competing stability between the alkene and where you want that carbocation to be. So yeah. Yeah. Okay, yeah, I'm not sure. This is a tough question, and maybe one that we can come back to, or you guys might find it good to ask about in office hours maybe. Dr. Tong might be able to give a good answer to this, or this might be one where you just have to actually compare the energies. Like you just have to go into a chart and find like what the two different energies of the molecule are, and compare them that way. So, okay. Yeah, again.
I have another question with which was like, I know in lecture we were talking about like 1,2 versus 1,4. So is that something, and that's for conjugated dienes. So when we have, right, two double bonds. So I don't know if this is the correct like logic, but like, could you kind of just like number within the conjugated system, like 1 through 4, and then if we were to predict the products, you would just put like your Br in this case on the second or the fourth carbon? Or is that like way too simplistic?
So, when you have just normal 1,3-butadiene, when you just have this, that's perfectly fine. In fact, even for Diels-Alder reactions, you can do that, and I even think that you should do that. For this example, it's more complicated because you have the kind of competing diene, you have the competing stability of the alkene and the carbocation where you want to put the carbocation. So it's harder, it's kind of harder to say. Yeah.
One more question is like, let's say we had 1,5-dihexene, and would that just be two separated addition reactions since they're not conjugated?
Yes.
Oh, okay, got it.
Yeah.
Thank you.
It would be.
In the case where there's multiple conjugated double bonds, for the thermodynamically favored, we'll go through all of the resonance and there'll be like a bunch of different products, or it'll just go through like, it'll just keep resonating and then just pick one product, like how do you?
So if I'm understanding, do you mean something like this, like a molecule like this one?
And then when it does the resonance, does it do, like for the thermodynamic one, does it go through each resonance structure and then make a product?
It would go all the way at the ends.
Okay.
Yeah.
Cool.
That way you would get the most di-substituted double bonds, and that's the most stable. So yeah.
Okay.
Yeah. So not that it's like something that we should dwell on for a long time, but for this example above, I am leaning on the side that this is the more stable, or this is the preferred product. This is an allylic carbocation, and the difference between a secondary and tertiary allylic carbocation is pretty minor and negligible compared to the difference in stability of this alkene. So I think that this is probably still the preferred product, but it's like, it's pretty specific. So we don't have to worry about that much. Okay. But we've hardly gotten into Diels-Alder. So why don't I just tell you guys the important part of Diels-Alder, at least like the way that you can kind of do it, like you can kind of go through Diels-Alder without really knowing Diels-Alder. You need to know it anyway, but whatever. So again, remember that with Diels-Alder, we have this diene, right? And we could draw, for example, this hydrogen, and I don't know, let's draw like some O-methyls or something, right? And let's say that we'd want to do a Diels-Alder reaction between this and, let's say a molecule that looks like this. Okay, this is like a really common type of setup that you might see for a Diels-Alder reaction. All right. This is actually, let me make it even more interesting. Let me get to this right here. Get rid of this. I changed my mind. I'm going to get rid of the top one because that's going to make it really hard for us. Okay. So let's say we have this reaction right here. All right. First things first. Anything that's on the dienophile, we have to move over to the other side. It has to be facing into the other molecule. Okay. So I'll say the dienophile substituent faces the diene. Okay. It makes our lives way easier. So let's rewrite this problem. Okay. And let me rewrite it here because I have space. Okay. And maybe for now, we're not going to worry about the hydrogens so much because they come in later. So we have this, and okay, we flipped our molecule, right? And maybe you're telling me like, oh, why are you making such a big deal out of just flipping the molecule? It's not that complicated. We've been able to do that forever. It's very helpful, and I promise you, the only way to success with these reactions is to take them very slowly. Okay, good. Now, let's say we were to add these two together. Okay. Remember, we make our ring, right? We get this goes here, this goes here, this goes here. We make our ring, right? We get a double bond there. Okay. Let's say we were to do that. Then we get this product. What do you notice about these two substituents? How are they positioned relative to one another?
Are they trans?
Let me phrase it another way. Or let me, that was a confusing question. Huh?
Is it ortho? I forget which ones there are.
Ortho doesn't come up yet. So endo, this one here is going to be endo. I phrased my question really poorly. So this is these two are going to be 1,3 substituted. Okay.
Don't you have to? Don't you have to line up like the partial negative, partial positive before you add them together?
Exactly. So the point is, if you ever get a 1,3 substituted product, you did it wrong. Okay, like you cannot get 1,3 substituted products, as far as I'm aware, in all of the problems that I've ever seen. If you have some really freaky substituents, maybe something bad can happen. So the full and proper way to do it is to line up all the positive and negative charges. But as a general rule of thumb, in every case that I've ever seen, it has been totally okay to just check what the product is. If it's 1,3, it's not right. Flip one of your two molecules and you'll get the right product. So now that means we have to flip our molecule. So let's do that. Let's just flip it. We'll rewrite the whole problem like this. Okay. And now we're free to add. So we'll go ahead and make our ring. Okay. And let me actually draw this a different way because I haven't done these in a while. So I'm not used to how I should usually draw them anyway. There's a common trick, and this is like one of the few times that I'll actually praise the textbook because there's a really nice example in the textbook. It's solved example 15.1, I think, where they show you that what you can do is you can just pretend that these two hydrogens are one. They're one unit. Okay. And we stick this whole molecule underneath those hydrogens. And so if I draw that out, and I haven't drawn one of these in ages, so it looks like this, okay? We treat these two hydrogens as big flagpoles, and they stand way up, okay? If they were like one carbon, like one unit, the whole thing would just point straight up. Okay, and now look, there's a double bond here, okay? That one, sure, we know. This thing sticks, it remains where it was. And then this, look, we did all the work earlier. This whole, whatever, this group is, whatever it's called, right? This thing points down because it was on the inside. Okay, this is pointing down. All right. And so that's what you can do. And I know for other sections of Orgo, drawing something that looks like this would be totally okay and accepted as an answer. If you want, or if Dr. Tong wants you to, you could draw this as a flat planar thing too, right? These hydrogens are both sticking up. And then, well, there's nothing over here. But down here, there's this guy. And down here, there's this one. Okay. And now look, these are 1, 2 substituted. Okay, good. That checks out.
Hey, Adam, could you quickly go over what you mean by like lining up the most positive and negative parts? Because I don't think we explicitly like went over that in lecture.
Yeah. Okay. See, I thought that Dr. Tong might have mentioned that in lecture. So with the proper way to do these, it's the way that takes extra work, but it's like if you want to be like full and proper and not use like cheap, dirty tricks. The full way to do this is you take your molecules and you draw out the resonance structures for them. So this O-methyl is an electron donating group, right? This oxygen has a whole ton of electrons. And so it can push electrons, and it pushes electrons all the way to the end of the molecule. So here's a plus charge, and there's the minus charge over here. So this side over here is minus charged. And then when you have, for example, this other molecule, Well, this group here is electron withdrawing, right? So it'll pull all these electrons away from the opposite end of the molecule. And so you could do resonance, and over here it's going to be plus charge. Okay. This is why we did that whole work earlier in flipping the molecule around. Okay. We flipped the molecule along this axis because we wanted this plus and this minus charge to be next to each other. This is a sort of opposites attracts kind of situation.
Got it. Thank you.
I kind of breezed right past that and didn't mention it when I was doing it up here, because if we get a 1-3 product, that always will mean that the opposites didn't line up. If we get a 1-2 or a 1-4 product, then we're good. We're okay. We're in the clear.
Adam, would you be willing to just do a simple curved arrow diagram of the Diaz-Zolder?
Yeah. Let me do that.
Wait, and
I'll
going
actually-
off of that, could you possibly go over the case of when we have like a pentene with 2 double bonds and you add something to it? Because I'm just having trouble seeing, knowing like whether the O bridge becomes like wedged or dashed, if that makes sense.
Okay. Yeah, that's a good, actually, I'll do a slightly modified example then. So why don't we do, it's a very similar example, but now it just has a carbon there instead of those 2 hydrogens. And the same other molecule. Let me make it an aldehyde because I'm a bit too lazy to write this every time. It's still electron withdrawing, it's okay. All right.
But just a quick question. You said it only works if you have like a 1-2, or was it a 1-4? Was the other one?
Yeah.
Okay.
Yeah. So you could remember it that way, or you could just remember if it's 1-3, something probably went wrong. Okay. Let me draw this out in 3 dimensions, so to speak, all ready to start. So I'm gonna, let me draw it like that. There we go. There's this first molecule, which is this pentadiene, cyclopentadiene. And I'll draw the other molecule kind of like wedging itself underneath. Okay. And so this molecule is kind of sliding underneath. And what happens is an arrow goes here. This arrow gets pushed over. And this double bond is used to make this bond between the 2 molecules as well. And so drawn out in this kind of like 3-dimensional way, these carbons stay up as earlier, but now we made a bond here, we made a bond here, and we keep that bond on the dienophile.
So the dienophile alkene is that curved arrow is going in to attach itself to that like corner, where the carbon that connects to the ether.
Yeah.
Oh.
So with arrows, or with colors rather, this is where the electrons are going. And I don't know, let's pick green. No, let's pick pink. Okay. So this is where these electrons all wind up. All right. in 3D, this is like, there's no like one good way to draw these things because the product is really inherently three-dimensional. There's no way to draw the product without it being in 3 dimensions, especially at least for a case like this. So, well, you know, it can be helpful to draw the reaction as it's happening like this. But there are also some times where, for example, you know, we could draw, let me do it down here a bit. Yeah, sure. So we could draw like this, plus this other guy, and we could just draw it on the page like this. The reason that I usually personally like drawing the product out this way is because then we're able to draw the whole thing with that comes out of the endo rule a lot nicer, and going from here to a ring structure is not going to be as bad. So why don't I finish drawing this one? Okay, let me finish drawing this structure, right? All that we had left was this O-methyl, and we have this aldehyde that's sticking down. Okay. If you really want, you could draw the other hydrogen that was there, right? Just to really remind you that, like, oh, this hydrogen is sticking up and the aldehyde is sticking down. Okay. And let me erase this. This is the same thing. Okay. So we just redraw. So now we could redraw it on the page, and we could draw, like, it's kind of ugly, but we could draw this carbon thing sticking up, and then the O-methyl and the aldehyde that are sticking down. Like that.
Is there ever a situation where a reaction won't be able to form the endo product?
I can't think of one.
Like, they should always be drawn into the page.
So, it's so I was about to mention this, but in case these reactions weren't bad enough, this product is racemic. So no, they shouldn't always be drawn into the page. Why is this racemic? I drew this coming in from underneath, right? If this is the diene, then the dienophile comes in this way. Okay. But there's nothing stopping it from coming in above. And if it comes in from above, then you'll wind up getting the racemic product.
Is there any way that you could possibly draw out the exo product as well? Because I guess I'm having some trouble like seeing the difference between the endo and the exo.
So the exo product would be if this aldehyde was on this side. Yeah. Let's see. Yeah, we would get.
That kind of makes sense. So it would be like if you have that carbon bridge and the aldehyde on the same, like both wedged or both dashed.
Yeah, exactly.
Okay.
Or to draw it in this sort of three-dimensional form, right? Everything on the molecule that this diene, everything here is all the same. We just get here that this would be the exo product, but we prefer not to form this, right? So actually, So the question about whether you always get the endo product, I think there's actually a question in the textbook, and I'm having a hard time remembering if that is the case. There is a question in the textbook, I think, where there's a molecule where you can only get the endo product, or something about it leads you to get specifically the endo product. You should check the problems at the end of chapter 15. It might be there, but I might be thinking about something that also comes up later in the course. So I would look into it, and if it is there, it's a good problem to do, but I can't remember exactly.
Also, do we have to consider the most stable chair conformation and stuff like this, or? Oh,
I don't think so. No.
Thank you.
Yeah, I can't think of a situation where that's come up. You don't quite have chair conformations and things like that, or it's like not as like conventional as you learned it last semester, because chair and boat and whatever you call it for 5 carbons, I don't remember, envelope or something, that's when you don't have double bonds. But when you do have double bonds, the whole like geometries will be different, and so we don't even bother thinking about it so much, I think.
Got it. Thank you.
Yeah.
Just to really quickly clarify, and I think Nicole just asked the same question, but so in the exo, the substituent, the aldehyde, and those 2 carbons that point up, or sorry, yeah, to form like the bond, those are both pointing up.
Exactly.
So exo is when, okay, the substituent on the dienophile and those of the diene that are forming that like bridgehead, those are pointing the same way. Okay.
Yeah. That is, if you're taking this dienophile again to attack from underneath. That's the way that I personally prefer it. I've always found that one to be more understandable, because then you have like the hydrogens or the carbon pointing up, and I always like to think of them as flagpoles. Yeah, if that's the case, if that's the way that you're doing it, you're having the dienophile attack from underneath, then yes, think about it that way. You don't have to think about it any other way.
That makes sense. I think he also was like in lecture, Dr. Tong was, I don't know if I completely understood him, but he was kind of equating the endo to where the substituent, in this case, the aldehyde, would be like axial. So it's not in the same, like spatial orientation as the diene, versus an exo, it would be like equatorial. So they're both pointing up.
Yeah.
Is that the correct? Okay, that was that.
In this case, that's true as well. So it sounds like Dr. Tong does the same thing, and I think most people do, where they have the dienophile come in from underneath. And because that's what we did, well, we have this dienophile. Oh, I guess actually either way that you do it, you'll have this you'll have this like this aldehyde, for example. You'll have it being axial instead of equatorial. So yeah, what Dr. Tong says was completely right.
Gotcha.
Yeah.
Could you clarify when you would know when it'll be axial, when it'll be equatorial then in this situation?
In that case, it'll be axial every time, because axial in this case will mean the same thing as endo.
Okay, but like, how would you said like to form the exo, you would have to move that carbonyl group to the other side? And I was like, how would that change it? I was kind of confused about.
So if you were making the exo product, then this carbonyl would be like equatorial here. It would it would be on this side over here. And so that means that whatever would be on this side would point down, and the carbonyl would be going up.
Oh, I get it now. Thank you. I didn't see that
Okay.
part.
Okay,
And
yeah.
Adam, didn't you say though that once you introduce an alkene, the whole idea of like kind of like axial equatorial gets weird because it's like a different geometry than what a chair
Yes.
or envelope would be?
Yes, it is.
Oh.
Yeah, especially in this case, like because there's this bridgehead carbon, it gets really pretty freaky. But when we do draw these out, there are some kind of hydrogens or substituents that look like they're axial and look like they're equatorial. So if that way of thinking works for you, use it and stick with it. Yeah, these reactions, I know I mentioned last week, and I was kind of signaling at the fact that like you're gonna learn the Diels-Alder reaction this week, and it's gonna be absolute hell. Yeah, it like this is really the situation where learning these kind of tricks and like these check boxes to keep in the back of your mind, it's really helpful because like I think two things about these reactions. First, you should like always take them really slowly, like super slowly, moving the molecule around. If you remember, like up here, when I was working this problem out earlier, we started with this withdrawing group over here on the top right. And if I was really fast, I could have just rotated this whole molecule around 180 degrees and it would have wound up right here. That's dangerous. That's risky. Just don't do it. It's like way too complicated for these problems. There's so many moving parts that like I at least certainly when I do these problems, I find it so much easier just to flip it one way at a time. Okay, move this part over to the left. It gives you the 1,3 product. That's no good. Okay. Well, flip the molecule the other way now too. Going really, really slowly like that is the best way to go about it, I think. And then my other main thing that I think about it is like remembering these kind of tricks, like never get 1,3 products. I don't know what else. Like you always want the withdrawing group to be facing into the other molecule, things like that. Okay. Should we do some problems?
Sure.
I realized that we spent a lot of time on review this time. I know Diels-Alder is like, for us, like the people who lead the workshops, it's like notoriously like a hard day. I mean, I like teaching with Diels-Alder because like I know this is something that is really confusing when you see it, and it's really the sort of situation where you need a lot of practice. And I mean, I think it's like helpful that I get to help you guys learn this. But it's complicated. I know it is, and practice will help a lot in this case. So in that case, why don't we start working on some problems? I know we have like 30 minutes, so I'll just move around between the rooms and we'll kind of work on them and talk about them.
And Adam, where can we find the workshop worksheet?
Yeah, so it's on the workshop canvas, the same canvas page that was used last semester. If you're not on there, I can add you.
Okay, I'm on there. Is it in like modules? Is it?
Yeah.
Yep. Sorry.
I put everything in the modules section. So we have a module for Dr. Tong's section, spring 2021 Tong, and I put everything in there organized by week. It's one big module.
Oh, okay, so workshop 2, chapter 15. Okay, got it. Thank you.
Yeah.
Adam, I've actually got to run, but will you be recording the part of workshop where you like go over the answers together?
Yeah, I can do that.
That would be helpful.
Okay, so I guess two things then. Well, so first, I always forget to do this. Can you guys just send your pen ID numbers in the chat? You could DM them to me or something. That way I can sign you guys in. That's helpful before we all go to breakout rooms. Okay. Other thing, so since we've spent the majority of this time reviewing and talking about that, it's kind of up to you guys how we want to do this. We could all work on the problems in one big group, and that way we'll get to go through and review all of them. Or should we still do breakout rooms? It's up to you guys. I'm
I'm
on.
fine as a group, but it's up to everyone else.
Okay.
Yeah, I think maybe I'm more so for the group.
Okay.
Thank you for going through all this because I don't know, after lecture I was a little confused.
Yeah, I know.
Yeah, I think this is a good week to maybe stay as a group.
Okay. Okay. Yeah, that's fine. Yeah, that's good. It's a tough topic. I was really trying to warn you guys last week. I know it's a really Diels Alder is a messy product, messy topic. So okay, why don't I get this going then? Here we go. I need to get the worksheet. Let me pull that up. I have it over here. Okay, and okay. Sure. Here we go. Cool. All right. So this first problem, which I will gently move up here. Great. Okay. So the question is to draw a complete MO diagram for cyclobutadienyl dication shown below. Okay. There's a circle here, which just means that it has two positive charges. So in other words, the molecule that we're interested in is, well, I'm not even going to bother drawing in the double bonds because there's 2 plus cations, so it's kind of complicated, but it's got these 8 orbitals, right? And there would normally be 2 double bonds, but we have +2 charge, so it's missing two electrons, right? So what we have is 2 electrons at the end of the day. Okay, good. So if we're drawing the MO diagram, well, this one is a cyclic molecule, and I wasn't really focusing on those so much earlier. But when it is a cyclic molecule, this one's kind of tougher to deal with. So what happens in that case? Okay. Again, we're going to have 4 molecular orbitals. That doesn't change. However many atoms there are, that's the number of molecular orbitals that you get. Okay, cool. Then what? We can't just draw like 4 energy levels anymore. It's a little bit more complicated and involved. So we have to use something instead that's called the Frost circle, which is something that you'll see next chapter. And this, I might not worry about it overwhelmingly for this quiz, but what you do for the Frost circle, which we'll definitely talk about more next week, is you draw the molecule, and then at each corner you draw a molecular orbital. Okay, and there are 2 electrons, so we fill in, and these are empty. This is bonding, non-bonding, and then anti-bonding. Okay. And then the question is, which of these is the HOMO and which is the LUMO?
Sorry, could you explain one more time how you got 4, like how you got like a square from the, I don't know, is it a hexagon?
So
Or I mean,
there are 4. Yeah. So the rule is always going to be there are 4 atoms, and so there are 4 molecular orbitals. I should say again, because we talked about it earlier, there are 4 atoms involved in the conjugated system. And so there are 4 molecular orbitals. You can think about, for example, just to give you another fun one, you could think about, for example, something like this with a plus charge, okay? Everything has a pi orbital, so this is a fully conjugated system. It's an ugly one, I'll give you that, but like, it counts, okay? And if we want to draw for this one, we draw energy, okay? Also up here. And there are 3 atoms, okay? So we have 3 molecular orbitals in the shape of the molecule.
So what dictates orientation of our shape? Like I get how there's 3, so there's a triangle, and then above there's 4 because it's a square, but
Yeah, that is a very good question, and it's one that's super hand wavy and there's no good explanation for. You always, so if there's an even number of points of vertices to your shape, then you want a point to be at the bottom. If there's an odd number, then you want an edge to be along the bottom. That's like a really crappy like reason. For example, if you have a pentagon, right? Here's, oh, that's not a good one for reasons that you don't know yet. If you have a pentagon, you draw it like this. Okay. If you have, on the other hand, a hexagon,
then you would
yeah,
want
then it would be a point like this. Okay, so you have all your molecular orbitals this way. Yeah, it's something that I don't think you guys have covered yet, and you'll probably see it next chapter, although it's often not officially covered as the frost circle. But this is like a common way that most other organic chemistry courses, like not at Penn, do it. And so this is like just the common trick to think about it. I maybe wouldn't worry about this problem so much for like this week's quiz. Because, oops, okay, sorry, I just have to do that. Because I think this chapter really only talked more about linear systems more than it did for circular cyclic conjugated systems. So why don't I just take care of these guys? Okay. Here's the important question, and it's really the only one that we care about. So which of these is the HOMO and the LUMO?
Would HOMO be the bottom, the like bottom shelf there?
Good. And then LUMO, well, both of these are LUMOs. They're both equally low, right? They're both unoccupied. These are the LUMOs. LUMOs with an S, sure. Okay. Good. Okay. In this case, if we're drawing out what those orbitals look like, plus, 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 minus, 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 minus on the bottom. Why don't I draw this in another spot? Here we go. Oops, wrong shape. Plus, 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 minus, 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 minus. Okay, great. Okay, up here. Oh, won't let me undo. So up here, it's not that complicated because, oh, well, it kind of is. I shouldn't even say that. Up here, we could draw through each of these, right? We get these 2 nodes, and so we get plus, minus, minus, plus, and then opposite on the way down. Okay, and for each of these, we draw 1 node going through the middle. with these cyclic systems, it's harder and more complicated to figure out where you draw the actual the nodes. So yeah, it is a tougher problem. Okay. Okay.
So for the one with 3 nodes though, would it be like an X and then like one that runs in between 2 of the orbitals?
These are all of them. There's no one with 3 nodes. And the reason is because we have 2 molecular orbitals, each of which have only 1 node.
Oh, okay. Oh,
So,
got it.
yeah. So in this case, it is different than a linear system. Yeah. So for this problem, it's weird. I didn't think that you would get any problems. It doesn't seem like you will get any problems about cyclic systems because, like, I mean, as you're already seeing, these are just more involved and they're harder to figure out. So I don't think that Dr. Tong would ask you about those without kind of prepping you. Or what you should do, and I would do it right now, but I want to keep moving through some problems. You should check in the textbook and see if there are any problems at the end of the chapter which have to do with circular conjugated systems and drawing the molecular orbitals for those. Or if you talk about it in like recitation or office hours or whatever, like of that sort. Okay. Sound good? Let's go. All right, let's get the next one on. And so we will take this question and we'll move it up here. Okay, here we go. So we have these 3 dienophiles. Why don't I even erase the second part of the question for now? We're not worried about so much. So we have these 3 dienophiles. Oh, there we go. And we want to rank them, their indicated carbon from most electrophilic, okay, or the most nucleophilic. What does most electrophilic mean in terms of the way we've been talking about it before?
Most positive.
Yeah, there we go. Exactly. Okay. So maybe there'll be some point where Dr. Tong tries to throw you off your game and you'll say most electrophilic instead of, or most nucleophilic instead of just positive and negative. So most negative. Great. Okay. So maybe at some point he'll try to throw you off your game like that. Just convert it to like what you know how to do in the problem, which is you know how to look at what's more positive or more negative, right? Think about these substituents as either pushing electrons towards the other end or pulling them away from that other end. So, for example, let's start with the ones that have substituents because they're more interesting, right? So this oxygen is pumping electrons into this thing. It's like pushing a whole bunch of electrons in. Okay, oxygen is an electron donor. It'll push electrons in towards it, right? So that means that these electrons will like to hop over here, and this will be negative. Okay.
Can you explain why it's an electron donor? I thought it was like really electronegative, so it takes electrons away.
So it's an electron donor. So even though it's electronegative, it's an electron donor because you can get a resonance structure with it. So you can do this. And this is like an okay structure. It's like a valid resonance structure. On the other hand, if we were to write, let's see. I don't even, well, we can't even write this structure because of the octet rule. Like this isn't even, this structure can't even happen.
Okay, okay.
Yeah. So it's just the fact that it has those extra electrons that it can donate.
So would that mean that oxygen is an electrophilic atom?
Well, it's I don't know. I'm not sure. That's like a. I'm not sure how I would reply to it because it's like an unusual way of describing oxygen in this case. I guess. Remember, with electrophilicity, we're thinking about how well it's able to like attack onto something that has a lot of electrons. In general, oxygen won't be, because the only time you'll find oxygen attacking onto something, it'll usually be giving its electrons and not taking them. So oxygens are really nucleophilic and not electrophilic atom.
Oh, because it's looking for a lack of electrons. It wouldn't attack something with electrons. It would attack something with a lack of.
Exactly. Yeah. It's a little bit weird up to this point. Well, maybe Dr. Tong has talked about electrophiles a bit, but up to this point in the course, you haven't really covered electrophiles very much. Like everything has always been about nucleophiles. They've taken center stage, SN1, SN2. They also are primarily what's involved in E1 and E2, right? And those are most of the reactions that you've really learned. Next week, we'll start learning about electrophilic reactions. And that is what makes it possible to do anything with benzene rings or aromatic rings in general. So you will get to see a whole ton of reactions that you could do with electrophilic stuff very shortly. Exciting, right? Okay. Here on this other side, we have this carbonyl, right? And this carbonyl sucks every electron it can in. It's going to pull electrons in from everywhere, from out here too. No, maybe not from out there, but it's going to always be pulling electrons in. And so this COO pulls electrons in. Okay, that means that this end over here is going to be more positive. Okay. Do I really need to tell you that this one over here is going to be in the middle? It's going to be like neutral? No, maybe not. It doesn't have anything either pushing electrons in or pulling electrons out, so it's going to be neutral, at least compared to the two. So maybe someone will say, yeah, well, this carbon chain is slightly electron donating. Yeah, it is, but it's very slight. It's very minor. So we're compared to this O-methyl group, it's nothing. It's like really weak. Okay. So again, we're going most positive to most negative. Okay, most positive would probably be the one that can actually hold a positive charge. Nothing crazy. In the middle is going to be this one, which doesn't have any kind of special resonance structures. And then most negative is this guy over here. Okay. This is the way that I personally really like to think about it, is in terms of pushing and pumping electrons in or pulling them out towards yourself. So that's like and for me at least, the nice way of thinking about dienophiles or dienes, both of them. It works the same way on either one. Whatever's attached will either push electrons in or pull them out. So. Okay. how about we check this next one? Here we go. Let me get it on the page. Oh, it's way up here. Okay. Oops, I just rotated it. Okay. So which side of the dienophile would be attacked by the diene during it deals Alder reaction? Okay. So, okay, I think it's asking in terms of what we just did above. Okay. So, okay, here there's an O-methyl group, right? Let's not think about this too hard. You could do the resonance. In fact, it's even good if you do, because you'll get a lot of practice with this and you'll like really remember where all of this comes from. But let's say we don't want to think that much, right? We have an O-methyl group. It pumps electrons in. Likes to push electrons away from it. So over here we'll have this minus charge. Okay. And so now let's draw in the rest of our structures. Okay. We had this structure over here. Is this diene going to attack carbon A or carbon B?
Doesn't matter.
It doesn't matter. Exactly. Why?
Because it's symmetrical dienophile.
Exactly. Okay. It's symmetric. Yeah, we could flip the molecule around. It's not going to really make a difference. The final product will differ because it'll determine whether this one over here in the like next to the methoxy group will be going in, or whether this one over here will be on the inside. So you can get multiple products, but here we wind up getting, yeah, we wind up getting 2 products. Depending on whether you have this or this. Okay. Or whether it attacks A or B. I think it doesn't make a difference, actually. I think just whether it attacks A or B is enough, but it's okay, whatever. Okay, let's see what else we had. So next we had, I think it was just an aldehyde, so it just looks like this. Okay, everything else was just totally normal. Oh, the aldehyde was on the same side as the methyl group. Okay, so now which side is it going to attack, A or B? Remember that this side was the partial positive charge.
A?
Yeah, exactly, right? Minus and plus. It's like, going to come up with a better combo. Yeah, right? There we go. These two are happy. Okay. Oops, wrong color, and I need to see what we had up here. Okay. Okay, and so we got a face.
Wait, sorry, how'd you get the double bond there and not like above?
Which double bond?
The one between A and B.
Oh, so I took this molecule, which I've at this point really screwed up, but I took this molecule and just redrew it. So it looked like this, and then I went and flipped it around this axis.
Okay, thank you.
Mhm.
So you did like the double bond like movement, like electron movement.
No, I actually didn't move a single electron. So I went and just took this molecule and just redrew it in this form. Like I just rotated it a little bit so it was actually standing upright. And then I just went and rotated it. Like here, these things are on the left, and over here, they were on the right.
Sorry, not that double bond. The double bond higher up, the one that was connected to the positive carbon that we talked about. Now you drew it. Oh wait, sorry, my bad. I just couldn't see it. Sorry, I see it.
Yeah, no, it's okay. For all of me talking about how you want to take these really slowly and move the molecule around really slowly, I went ahead and I did it really fast, which is not good. Yeah, this is the same exact thing as above. I just rotated it. Yeah. Okay, and then over here we had, again, we had both substituents on the same side, and over here we had a minus charge. Is this diene going to attack on carbon A or B?
B.
Okay. It might attack on B, but
Oh, are you talking about the third one here or the second one?
the third one, this one here.
Yeah, would attack on B.
So it would, but this reaction probably won't happen at all. Okay. So in this case, it'll be B if the reaction happens at all.
Is it because they're both nucleophilic?
Yes, exactly. Or in other words, you always want a diene that has, so you want donating. And on your dienophile, you always want withdrawing substituents. Does anybody remember why? This one's kind of involved. So when you have, it all has to do with the HOMO and LUMO and what their actual energy is. So here, remember here, this molecule, we're taking advantage of the HOMO of the diene. Okay, it's giving up its extra electrons. So you want to push those up higher in energy, because that way they'll just leave the molecule easier if they're higher in energy. Over here, we want a really low energy LUMO, unoccupied orbital, because that way it's low energy. The ones from over here on the diene will just happily go to somewhere that's really low in energy. And it just in general, a donating substituent will raise the position of the HOMO, and the withdrawing substituent will lower all of the orbitals really. So this. Yeah, write that down.
Sorry, what is that first word on the left side there? I see orbital
Raises.
HOMO energy. Raises.
Raises.
Got it. Thank you.
Yeah. Thanks for asking. My handwriting can get messy. Yeah, so really all the orbitals energies changes, but we really care about especially the HOMO and especially the LUMO. That's what we're interested in. Okay.
Could you also just quickly just write what the products would look like for each of these?
Yeah. So here's what we had, right? Here's our diene, and then let's say we have this structure right here. It doesn't matter which side is attacking where because it doesn't matter. So what's going to happen? In this case, we have these hydrogens and they're going to stick straight up like flagpoles. And this is the easiest way that I always think about it. So these hydrogens are sticking up like that. There's our double bond that we get. There's our O-methyl. There's only one spot it can go. And then we fill in the rest, okay? This hydrogen is pointing down with the carbon pointing up. And this carbon is pointing down with its hydrogen pointing up. Okay.
And how's that not exo? So isn't, because the carbon is going against.
So yeah, exactly. One of those carbons is exo, the other one is endo. But we can't rotate around that double bond, right? We're stuck like that. So this is the best we got.
Oh, but that's where the two products thing comes in, where
yeah,
the flipper
or
comes in.
Exactly. Or we flip this, and then we do the same thing over again. Okay, and we get our O-methyl like that, and now we just flip. Right now, this carbon is pointing down, and there's a hydrogen there in its place, and here there's the hydrogen. Okay, so we switch those two. Okay, why are these two not the same structure? What is different about them? What makes them be different at all?
The orientation of the methyl groups coming off of the alkenes.
Would
Yeah.
they be enantiomers?
So, would they be? I don't think they would be. I think they're actually diastereomers. I think. I think they are. It looks like it to me. What I'm getting at here is that the reason that they're two different molecules is just because this O-methyl is here. That's what, like, in some sense makes this asymmetric. It makes it like so that one side is different than the other side of the molecule, which is why I think these two are diastereomers. Right? And then you also get plus or minus of both of them.
But the dienophiles themselves are just the exact same molecule, right?
Yes, they are.
Okay.
Yeah. Yeah, so this is a situation where you have to write out R and S for every single thing if you want to be like extra sure, because I've kind of been saying this, but like if we want to be like 100% certain, we have to write out R and S for every single place. And how many stereo centers there are there? This is always just good practice. Well, there's one here, there's one here, one here, and one here. The same thing. Okay. And why was I making a whole big deal out of the fact that there's this O-methyl here? If, on the other hand, we were to have just this normal molecule, and we were to do this, then there's that hydrogen, there's that, right? We put in our double bond. Well, now we can get one methyl pointing down and the other one pointing up, or we can get this to happen. All right, and here's the methyl pointing down. And yeah, that's right. Okay. right? And after all this work, what you can do is that this molecule here can bend, right? You could take this and bring it down. And let me use a different color because this is just getting way too complicated. You could take this and bend it down, and this and bend it down, and these two and bend them up, and these two and also bend them up. And I think, although I could very well be wrong, that these two will just be enantiomers of each other. I think so. Or they'll be the same molecule and you'll get the enantiomer the other way, but it's something like that. I think so. Again, another situation where you just have to do R and S for each of the two stereocenters. This time there's only two to figure it out. In fact, yeah, they are. But yeah.
Quick question for the before when we were comparing the two and saying that they were diastereomers. So the two stereocenters that stay the same are those ones that are coming from the diene, right? And the ones that are coming from the dienophile change. So that's what makes them diastereomers. But if all of those stereocenters were to change, that's why you're saying doing RNS, then we would say enantiomers.
Yeah. So just always remember that two things are enantiomers. Like two things will only be enantiomers if every R and S is flipped between them. Yeah. Okay. Woo. It's a lot. Believe me, I know. Okay. It's like 1:10 and already people have gone. So I realize you guys want to get on with your Sundays and everything. So
Thank you.
I guess there's a Super Bowl or something happening today. I don't know. I don't really know anything about sports. There's an entire like remaining section of questions on the worksheet about predicting the product for the Diels-Alder reactions. Do them. Like, please do them. They're really helpful. It's good. Always good to practice a lot of these, and that's like the only way that you'll pick up on how it works. So.
When we do them, could we just throw you an email if we have any like questions about the key that you throw up?
Yeah, absolutely.
Awesome.
Or send me a Canvas notification or whatever form of communication works for you.
Got it.
Yep. Awesome.
Thank you